Where is the field of biomechanics headed over the next decade? What would it take for biomechanics to play an essential role in the booming digital health movement? My name is Melissa Boswell, a postdoctoral fellow in bioengineering at Stanford University. Through my recently completed PhD, I worked on mobile biomechanics projects, collaborated across different fields, and simply had the pleasure of attending inspiring talks or interviewing amazing biomechanists. These experiences have led to exciting visions for the future of movement analysis. I'm going to share some of these ideas for translating biomechanical analyses into real-world settings. I hope this talk opens up more conversations about how we can make the largest impact in biomechanics. So I'm excited to hear from you and form a collaborative perspective on where the field is going and how to get there. Many of us entered the field of biomechanics to help people by supporting better, healthier movement and overall more fulfilling lives. And we know from decades of research that assessing one's biomechanics can help us identify, understand, and design treatments for diseases and disorders that affect movement. While we've just learned more about the history of biomechanics and how far it has come, historically, we've still been constrained to a biomechanics laboratory equipped with motion capture cameras, force plates, and other expensive technology. This barrier poses a challenge to access biomechanics and intervene to improve health and functioning at a global scale. In fact, the median number of participants in biomechanics studies ranges from 12 to 18. On the other hand, harnessing data from commodity technology like smartphones has allowed studies to analyze movement data from hundreds of thousands of people. But this data has been restricted to measures like step count, with little insight into important biomechanical parameters. Where I see motion analysis going is somewhere between these. I think there is still a place for accurate and precise technical equipment in a laboratory setting and massive data sets with lower fidelity data. But I'm excited for the future where we can bridge this gap between these extremes, collecting higher fidelity biomechanical measures from scalable and inexpensive technology. I believe this combination will make a significant impact on global health. Let's consider the simple task of going from sitting to standing. This is actually one of the most mechanically demanding tasks of everyday life. Yet it is essential for functional independence as it's needed for tasks like standing up from a bed or a toilet. Sit-to-stand transition tests are widely used in clinics to test physical function. But only timing is quantified, and typically by a stopwatch. However, movement is a key determinant of sit-to-stand strategies. And in fact, kinematics of the sit-to-stand test, like joint angle ranges and velocities, are related to a number of health factors, including frailty, age, and osteoarthritis. So while timing of a sit-to-stand transition is indicative of physical function, this can be influenced by a wide range of diseases, injuries, or demographics like age. Kinematics, on the other hand, can give additional insights that are more sensitive and specific to certain conditions. So what do we need to focus on to make these more insightful biomechanical measures an accessible biomarker? While there are many things that I think will contribute to this vision, I'm going to discuss 3 components today that I believe are essential to making it a reality. The first is leveraging advancements in data science and computer science. The second is creating scalable and inexpensive platforms for disseminating biomechanical assessments. And the third is collecting larger and more diverse data sets in parallel with other biomarkers and measures of health. So I'll start with this first component. In recent years, there has been tremendous growth in tools that enable movement analysis outside of the lab. Things such as inertial measurement units, electromyographic sensors, pressure insoles, and pose estimation. But all of these tools have limitations ranging from sensitivities to placement, unclear relationships to health, and general inaccuracies, whether due to issues like drift or algorithm robustness. And due to these limitations, in many cases, the data from wearable sensors are not sufficiently accurate for certain research and medical applications. However, these tools have improved a lot in a short period of time. The use of data science methods in human movement biomechanics has played a large role in this, And you can see from this plot that studies that focus on neuromuscular and musculoskeletal pathologies have increased exponentially in recent years. We can leverage these advancements by using new machine learning methods to improve upon current out-of-the-box sensors and algorithms. For example, Newell and colleagues developed a network for pose estimation consisting of multiple stacked hourglass modules which allow for repeated bottom-up, top-down inference. This method was substantially more robust, including with heavy occlusion and multiple people in close proximity. We can also implement emerging sensor fusion techniques, such as the extended Kalman filter, to combine multiple sensor outputs and improve overall accuracy. This can include multiple sensors, like multiple IMUs, but also combining things like IMUs and pose estimation from video. The sensors mentioned so far measure what is happening from outside of the body. While this is useful, what is likely more useful and what we really want to get at are measures of internal joint loading and muscle activation. Advancements in computer science also contribute to advancements in modeling and simulation, where we can get to these internal measures. These models will also continue to improve with things like novel imaging technologies and other methods to better characterize things like tissue properties, as well as create more personalized models. We are also beginning to drive these models with outputs from sensors like IMUs and pose estimation, rather than requiring motion capture. For example, Alborno and O'Day and colleagues developed the workflow OpenSense to compute IMU-based estimates of kinematics using sensor fusion and an inverse kinematics approach with a constrained biomechanical model. And from that could estimate lower extremity joint kinematics from IMU data that was accurate and capable of assessing and mitigating drift. One really beautiful example of this is a technology that was recently developed by Antoine Felice, Scott Ulrich, and Łukasz Kaczynski, called OpenCap, which they are presenting at this conference. They start with pose estimation with 2 cameras and then triangulation to determine 3D video key points. Then an LSTM model transforms these key points to an anatomical marker set, which is input into an OpenSim musculoskeletal model. The dynamic simulation tracks the augmented marker set, and from that outputs kinetics. It's exciting to see a lot of different advancements coming together, and this type of technology is really promising. As a side note, I also wanted to say that we took OpenCap to an outreach event for middle school students at the park, and we captured one of the students performing some volleyball moves. The students and parents were really excited to then see it play back as a musculoskeletal simulation. So another cool thing about mobile biomechanical tools are the ability to demonstrate and educate and get the next generation of scientists who will be tackling these challenges excited about biomechanics. So we're making massive strides in data and computer science applied to biomechanics. But how do we disseminate this technology at a large scale? I want to start by sharing an example of this. In a recent study, Łukasz Kaczynski and I developed a mobile biomechanics assessment that individuals participated in nationwide. We created a web app, the main page is shown here, in which individuals self-recorded a video performing the sit-to-stand test at home, and they submitted it to an automated pipeline that is also that uses pose estimation to evaluate kinematics. With very minimal researcher time or resources, close to 500 individuals successfully participated in the study at home from 35 US states. And from the user side, this looked like going to our website, sit2stand.ai, to join the study from their smartphone or tablet. They completed a series of questionnaires to make sure they qualified and the study was safe for them, and they also completed a digital consent form which was approved by the IRB. They then got a video and written descriptions of the test instructions and an option to record or upload the test. They were then immediately directed to a health survey, and then the pipeline automatically performed pose estimation, calculating timing and biomechanical parameters like trunk flexion. It also returned the video with pose estimation overlaid to participants, which they said that they enjoyed. Part of what I think made this application successful is that we took learnings from other fields to make the interface and the instructions for self-guided participation as simple and clear as possible. We also ran multiple pilot tests and had many iterations of refinement before launching the nationwide study. So while we are starting to develop tools like this that can be used at home or in clinical settings, I would still argue that the most rapid application of digital biomechanics technology is in industry. This is a great sign for biomechanics, though. Movement is so essential to humans thriving, and companies are finally recognizing the role that biomechanics plays in this. However, this isn't to say that these are the most advanced or accurate technologies. And in fact, I've sometimes found myself frustrated at the claims companies are making. Things like calculating calorie burn from heart rate, predicting falls, and even prescribing movement patterns claimed to be healthier during exercise. Most of these claims are unvalidated. Yet, these technologies are much more widely disseminated in lay populations than the technology developed for academic research purposes. While I strongly value and acknowledge the need for freely accessible technologies in research settings, I also believe that collaborating with the emerging motion analysis companies can supplement our traditional approaches to research and be mutually beneficial. Many companies are already doing a fantastic job of creating easy-to-use platforms for individuals to monitor and assess their movement, which can be used to disseminate for our own research studies or as inspiration for new technology. And these companies can benefit from our expertise in study design, including creating and testing clear hypotheses and the latest advancements and discoveries in biomechanics. I think we can and should work to find creative ways to come together that also support open science and data sharing so that we can continue to refine and improve emerging technology. From my experience working for and collaborating with some of these companies, I found that one of the biggest benefits they have are their resources. Not just monetary, although it's a significant contributor to their success, but also with large interdisciplinary teams that all work together to quickly push products forward. I also think they do a good job of implementing emerging biomechanical technologies into already existing commodity technology that leads to more inexpensive and accessible tools. So these points are also some things to consider when designing new digital tools. Finally, as we are disseminating this technology, we need to collect larger and more diverse datasets alongside other biomarkers. As we collect high-dimensional and heterogeneous datasets, we can begin to test new relationships and investigate mechanistic causes of health and performance. I think it's also important to mention the need to have more representative and diverse samples, which is more possible with mobile tools. Similar to other scientific fields, only in the past decade or so has the field of biomechanics worked to bridge the gender gap in research studies, which were historically mostly focused on males. Addressing the large gap in racially and ethnically diverse samples is only in its infancy. While these challenges point to larger societal issues that I won't try to breach here, I believe it's important to emphasize that making biomechanical assessments accessible allows for larger and more diverse data sets. I also want to mention that we should continue to prioritize data sharing so we can build even larger data sets and help the community learn together. There are now some great data sets, but data sharing needs to become the norm in order to advance the field. So evidence of what we can find with larger data sets is seen in the results from our sit-to-stand study, where with our large and diverse data set, we found relationships between health and demographic measures like biomechanical parameters. So for example, a higher maximum trunk flexion, or how far forward a person leans to stand up, was related to a diagnosis of hip or knee osteoarthritis. Trunk flexion also varied across ethnicities. And in individuals 50 years of age and older, greater forward trunk acceleration was associated with higher mental health. All of these relationships remain true, even when controlling for age, sex, BMI, and physical health. However, there may be underlying factors contributing to these results that we did not capture, especially with race and ethnicity, which is likely due to underlying health inequities. Importantly, though, these measures were not related to time to complete the test, confirming our hypothesis that quantifying biomechanics leads to deeper health insights than the typical timing measure obtainable in a clinical or at-home setting. I want to conclude with a final figure that sums up the ideas just presented and incorporates a few additional points. It's adapted from a recent perspective from our team, focusing on leveraging mobile technology for scalable public health promotion, and is under review at Annual Review of Public Health. An individual is an entire system of different processes. This includes biomechanics, but it also includes things like their psychology, physiology, and behavior. Together, these form a more holistic picture. And we can add additional data about the environment, such as the natural surroundings, weather, and the social and built environments. This helps us zoom out to additional factors that may be influencing an individual. We can then take this data and use data science to interpret the data and develop predictive models and computer science to build personalized musculoskeletal models. And then we can work with experts in human-computer interaction to improve accessibility, and behavior scientists and psychologists to improve engagement with potential biomechanical interventions. And then this information can feed back to the user as personalized interventions or health predictions. And we can see that this process will continue to iterate, and biomechanics has a very exciting role to play. So in summary, I believe that advancements in data and computer science, scalable and inexpensive platforms for dissemination, and larger and more diverse data sets in parallel with other biomarkers are essential to the future of movement analysis. As an additional point, while this talk offered insight into the scientific aspects that can progress our field forward, just as essential, if not more essential, is that we prioritize inclusion and diversity in science and research. I'm happy to see communities forming to support this, such as the International Women in Biomechanics, Latinx in Biomechanics, and the Black Biomechanists Association. On the podcast, Biomechanics on Our Minds, Hannah O'Day and I facilitate conversations on this. Just this month, we released an episode with Robin Queen where we discuss why we need more racially diverse study samples and ideas for overcoming obstacles to this. There is currently an ever-expanding network of digital metrics, particularly those surrounding one's health. Putting these new tools and methods together, we can start to picture how biomechanical measures can fit into that network. We can combine with other insights such as anthropometry, and supplement with field knowledge of biomechanical underpinnings and mechanisms, and the effects of past injuries, diseases, and health risks to build a more expansive understanding of one's health. So thank you to Dr. Brian Davis, who gave the first part of this duo talk and was my undergraduate advisor at the University of Akron. He was the first person to really spark my interest in biomechanics, so it's been an honor to present alongside him. Thank you to my advisor, Scott Delp, and to my lab for their support. Thank you to the International Society of Biomechanics for putting together this special session, and congratulations on the 50th anniversary. And finally, thank you to the World Congress of Biomechanics for putting together such a fantastic event where we can reflect on the past, learn about the latest work, and be inspired for the future of biomechanics.